Brian. Okay, Fee. Thank you. EJ. Go. Hongwei. Sadik. Ran. Michael McDowell. Thank you, Ran. Thank you, Michael. Trong. Hong Lin. I knew there was a reason why he didn't say he weren't here when I called out Hongwei. It's not because he's not here. Valeria. Hi. Asya. Hassan Safwan. Okay, Reniko, I know you're here. Carla. Shubham is here. James. Prem is here. Thank you. Claudia. Thank you. Kiefer is here. Ray Fong. Thank you. Hayden. Thank you. And Lishui. Okay. Anybody I didn't call? Okay. Oh. Aaron. Thank you, Aaron. Okay. So what we're gonna do today is we're gonna have our presentation, and then we're kind of get started on just the 3D and just how to draw 3D. You're gonna do some of the exercises that you had done in 2D. You're gonna do them now and try them out in 3D. So that will be today's session. Other than that, we're not gonna go into the project. I am gonna be, because I just received your projects, on Tuesday. I'll be marking them, and you should have them back by Tuesday, and then we'll get started. You can get started with your project number 2. Okay. Now, any questions about that? Okay. So for your presentations, some of you, the first 4 groups I've already marked, so you guys see your marks. Now I want to let you know, so I'm going to be marking them as we go. So for like group 5, you'll have it before next week. You'll already know your mark, but just to let everybody know that your marks for the presentation can change and may change in the individual portion of it. So when you actually open up and you see the details, I gave everybody full marks right now for those. But if you're not, participating, or you're not coming to class for the presentations and showing your support to the other students, then these marks will come down. Right? If you're not asking questions and being, participating within that group, within the presentations that are coming up, or not answering questions within your own presentations, if you're asked a question, or, trying to just have one person do everything, this will all show up on your individual marks. Okay, so that's what I was talking about from before. So right now you'll see everybody has the same mark, but that can and may fluctuate depending on how much you participate in all the presentations. And most, I'm not saying, of course, not everybody has a question for every single little thing. And I understand that. And missing a class once in a while, for whatever reasons, with your presentations, I can understand that. But on a consistent basis, that's where it shows me, that's where the difference is, okay? Any questions about that? The first 4 groups, were you guys happy with your marks? No? No questions, or no? James, did you even do your thing yet? Okay. All right. So, sorry, who said was going to do the presentation? Who is going to have? Okay, thank you. Let me give you presentation rights here. Okay, so Belgan, you can go ahead and get started. I'm going to mute myself. Okay, good luck, guys. You can start sharing your screen. Do you know how, by the way?
Yes. Can you hear me?
Yes, I can. Perfect. Thank you.
Okay, thank you.
Hi, can everyone hear me?
Yes, we
Yes,
can.
yes,
Yeah,
yes.
okay. Hi, everyone. We're group 5, and we're going to be presenting on retained soil system walls. My name is Renique Samuel, and the other group members are Bill Gundash George, Pramalan Thiagaraja, Kifa Ware, and Shupam. Next slide. A RSS wall is a structure composing of alternating layers of compacted backfill and soil-reinforced elements that are fixed to a wall facing. The stability of the system is provided by the backfill and soil reinforcements. The resulting structure is flexible and can carry various loads. RSS walls are also known as mechanically stabilized earth walls, MSE or MSEW for short. Next slide, please. There are 3 main parts of RSS walls: the facing, soil reinforcements, and the select backfill. Next slide, please. There are numerous types of facing available that you can see in the images here. The facing is typically made of precast concrete or wire mesh. The different types of facing shown are full height, cruciform, rectangular, permanent and temporary wire mesh, and integrated with traffic barrier. Next slide, please. The soil reinforcements are typically made of steel or geosynthetic in the form of strip or ladders. There are 3 types showing here: ribbed reinforcing strips, which are 2-inch wide and bolted connection to facing elements; high adherence ladder, which are 4 inches wide and have a clevis loop connection to the facing element; and 2 wire wide ladders, which are 9 inches wide and are ideal for short walls. Next slide, please. Select backfill allows for reliable construction and performance of the wall, and it is chosen based on several factors. It can be obtained on-site or from a distributor. Backfill can be soil, which is usually sand or crushed stone, recycled material from crushed stone or other materials, lightweight, which is lightweight aggregate, low-density cellular concrete, or foamed glass concrete. I will now hand it over to Kiefer to go into further detail about RSS wall and components.
Thank you, Renique. Can everybody hear me?
Yes, yes, brother.
All right. So, the RSS wall is a simple structure formed by select backfill, galvanized steel high adherence, reinforcing ladders, and geosynthetic reinforcement straps. These reinforcements are used to generate friction on the soil. Moreover, the facing of the RSS wall helps to prevent the erosion of the backfill and gives the attractive appearance, which can be used as concrete or wire mesh facing. Other components that form the reinforced earth structure is the leveling pads as a flat starting surface for placing panels at the first course, and the precast copings, which is placed at the end of the construction and the top of the precast concrete panel if it is required of the project. The connection of reinforced earth facing panels and reinforcements is made up of tie strip and structural galvanized high strength nut, bolt, and washer. The components, which are firstly the backfill, which has to meet the mechanic and gradation safe size of 0.0075 millimeters and cannot be more than 8% passing. It should be well graded, free draining, and non-frost susceptible. The The friction and unit weight also has to meet the specific requirements of the electrochemical properties. Secondly, we have the galvanized steel reinforcement, namely the HA steel strip and the HA ladder. The HA steel strip is a perfect solution for high static and dynamic design loads, high walls, bridge abutments, heavy duty mining, and industrial retaining wall railway. The strips may be galvanized or black and are designed to be bolted to the tie strips at the back of each facing panel. These are ribbed strip which are designed to create friction with the soil mass. They are also typically supplied in 50 mm width and varying length according to the design of the structure. The HA ladder are extreme pullout has an extreme pullout variation and is perfect for structures up to 6 meters. Thirdly, we have the geosynthetic reinforcement, which comprises of the geomega reinforcement, the eco strap reinforcement, and the HA eco strap reinforcement. The reinforcing geosynthetics can be made of high density polyethylene, polyester, and poly, then becomes an efficient solution when the chemical characteristics of the backfill are not suitable to the utilization of galvanized steel. The geomega reinforcement system allows for construction in chemically aggressive environments such as marine environments, corrosive backfilling materials, recycled aggregates, pollution risks, infiltration of the de-icing salts, etc., etc. This system uses a geostrap type of reinforcement made of polyester tendons and is used when the reinforced earth structure is affected by chloride or sulfates and low pH environments. The EcoStrap reinforcement is a polyvinyl alcohol PVA tendon which is used when the backfill has high pH, and this has the capacity to support higher temperature. We will move on to the facing where we have the concrete and the wire mesh facing. The precast concrete facing is panels which are produced in standard sizes in order to meet the elevation of the structure and the construction procedure. Depending on the height of the geometric requirement for a specific project, the reinforced earth structure can be fabricated with some customized panels. The wire mesh facing is a lightweight, very flexible, and has the ability to accommodate large settlements erected by hand, eliminating the need for heavy lifting equipment. The wire facing can be provided with fabric or rock facing according to the service life of the project requirements. We then have the fasteners, which are galvanized structural bolts, nuts, and washers. These are elements to make connections between the facing panels and the galvanized steel reinforcement. The size of these fasteners are usually 30 mm in length or ½ inch in diameter. Lastly, we have the concrete leveling pad, which are unreinforced concrete non-structural elements 150 mm deep by 300 mm wide. Bill, next slide, please. The lifespan of an RSS wall includes those at pile-supported abutments are designed for 75-year service life. Those used in bridges are designed for 100-year service life. Temporary walls can be designed for a few years. They can later be permanent parts of the structure. And we will now move on to Bill Gundashdorj, who will explain the construction of RSS walls. Thank you.
Thank you, Kiefer. Now I'll be talking about the construction process of RSS walls. Construction process of RSS walls consists of several steps outlined below. Foundation leveling, base leveling, panel installation, soil reinforcement installation, drainage installation, retained soil backfilling, and layer by layer compaction. Foundation leveling, aka the preparation of subgrade, is the process of removing unsuitable materials from the area to be occupied by the retaining wall structure and removing organic matter such as vegetation and other unstable materials to grade and compact the subgrade. In not so stable foundation areas, ground improvement methods like dynamic compaction, stone columns, or other foundation stabilization and improvements must be made prior to RSS wall construction. Base leveling. Prior to erection and installation of the first row of panels, a concrete leveling pad of 200 millimeters or 1 foot wide by 150 millimeters or 6-inch thick must be placed underneath the panels, which acts as a guide for the face panels. Once the area has been properly prepared, an unreinforced concrete leveling pad is put in place or a precast pad is placed. The leveling pad concrete must cure for a minimum of 12 hours before placement of the wall face panels can begin. Even though the leveling pad is not structurally important, it's still important to the construction of the RSS wall. The leveling pad sets the horizontal and vertical alignments of the wall. It must be in the correct horizontal position, level, and at the correct grade. In addition, no more than 2 shims, each 5 millimeters thick, should be required to level the panels on the leveling pad. If the wall is not level, the panels will bind against each other, causing spalling of the edges and corners. Panel erection and installation is a simultaneous process with fill reinforcement and retained backfill placement. Panel erection. Face panels of RSS walls consist of either precast concrete panels, metal facing panels, or dry cast modular blocks. The first row of facing panels may be full or half-height panels, depending upon the type of facing panel used. First row of panels must be shored up to maintain stability and alignment, whereas in construction with modular dry cast blocks, full-size blocks are used throughout the span with no shoring. Face panels are carefully placed on the concrete leveling pads with a crane lift and must be secured with steel bars, aka reinforcing rebars, to the reserved holes or hooks on each panel to connect the adjacent panels together. Reinforcing elements such as the steel bars and structural rebars must be placed in strict compliance with spacing and length requirements in the design drawings. In addition, misaligned vertical or horizontal openings can result in face panel misalignment and cracking or spalling due to point stresses. To mitigate this, bearing pads made of cork, neoprene, or rubber are typically used on the horizontal joints to prevent point stresses. Other joint materials such as synthetic foams and geotextile joint covers are used along the vertical and horizontal joints to prevent erosional fill through the face panel joints. All materials mentioned above are installed in accordance with the design, especially in regard to thicknesses and quantity. Soil reinforcements. During the erection of first row of face panels, the first layer of fill must be placed consistently and compacted to a specific density, usually around 95 to 100%, with specific range for moisture contents. Compacted and reinforced fill thicknesses are controlled based on specification requirements in addition to vertical distribution of reinforcement elements. Typically, each layer of fill is compacted with a thickness of 30 centimeters or 1 foot. The reinforced fill is compacted with a smooth-wheeled roller weighing not more than 8 tons, and the compaction machinery used within 1 meter or 3 feet from the walls should be a vibratory roller or a plate roller weighing less than 450 kilograms or 1,000 pounds. Each RSS reinforced fills have unique facing connection, details, and must be made in accordance with the manufacturer's recommendations. Reinforcements such as flexible geotextiles and geogrids usually require pre-tensioning to remove slack in the reinforcements or in the face panels. The same tension is then maintained by staking or placement of fill during tensioning, which will reduce the potential of subsequent horizontal movements of the panels as the wall fill is placed. Simultaneously, drainage mediums are placed and spread behind the wall with adequate slopes to nearby drainage pipes, which flows to nearby storm sewers or drains. And here we have a quick recap video to better illustrate the construction. Now I will hand it off to Shubham to cover the different application RSS walls are used for.
I'm sorry. Good afternoon, ma'am, and everybody. Thanks, Bill. I will proceed further. Phased construction. The first application of the RS wall is phased construction. Is a kind of construction where we need a short length to be constructed quickly and as soon as we can get the road ready for the transportation. So for phased construction, RSS walls are more suitable. And then arc bridges. Arc is a irregular shape in which we don't have a regular perfect square or rectangular shape panels. So this disadvantage of the traditional RSS wall is we can give that any shape we want. So as these are precast concrete structures, the panels, so we can order them. We can have any kind of kind of structure we want for the arch bridges, and then bridge abutments in minimizing the right of way of embankments. So embankments is a heap of soil. So if we are using the RSS walls, that there is a 90-degree the vertical wall, so that doesn't have to be given a slope on outer side. So it's a saving of the road right of way, and slope stabilizations. It's more efficient in stabilizing the slope, and heavy construction loads, as these panels are interconnected. Uh, Bill already have mentioned it, how those are connected, the procedures. That's a more effective way to connect the panels, and that takes more loads. So this is all the applications are for the RSS walls. And now next slide, please. Yeah. So phase construction already mentioned here. So there's a pedestrian bridge. So we will go through this video. That's a quick video of 100 seconds, I think. And I would request Bill to play this video, and we will have a look on this, please. Thanks, Bill. So it's a bridge, pedestrian bridge. We can see. So I would request Bill to pause the video for a second. So in the description here on the left side, we can see the installation time of the bridge is just 1 week. So that's pretty like very short period of time. If we talk about the reinforced concrete structures, which are like the steel bars, that takes a lot of time. Minimum 15 days are required uh, to open the scaffolding, and it takes space. We can't let the traffic run under the bridge if we have the scaffolding. So it's very quick, and if there is a time saving is more being done in these type of walls. So that's a saving of money, and that's an economical plan. Bill, go ahead. Now my fellow Kiefer would take you guys to the components and RSS in the urban Ontario. I would request Kiefer to take on.
Thank you. The RSS wall is a solution for Ontario's urban transportation system because this retaining wall is designed to support the earth's pressures as well as the heavily concentrated vertical and horizontal loads imposed by the bridge's superstructure. For bridge abutment, there are two types of used abutments. That's the true abutment and the false abutment. The true abutment supports the horizontal and the vertical load applied at the bridge seat, and for false abutments, the bridge seat is supported on piles. In this case, when piles are necessary, reinforcing strips can be placed between them as they are easily diverted. A retaining wall generally is a structure designed and constructed to resist the lateral pressure of soil when there is a desired change in the ground elevation that exceeds the angle of repose of the soil. Retaining walls are an economical way to meet everyday earth retention needs for highway and bridge grade separations, railroads, and mass transit systems also. They are also used in response to difficult design conditions such as very high structures and restricted spaces where obstruction within the MSE soil mass are present. Um, I will now move on to Premelon, who's going to speak on the bill next. Yeah, on the modes of failure in RSS walls.
Thank you, Kiefer. Can you guys hear me?
Yep, we are
Yeah.
there.
All right, cool. So modes of failure. To design retaining soil systems, it is important to define failure and to understand how walls can fail. Under static conditions, retaining walls are acted upon by body forces related to the mass of the wall by soil pressures and external forces. A properly designed wall will achieve equilibrium without causing shear stress that approaches the shear strength of the soil. However, inertial forces and changes in soil strength may violate equilibrium and cause permanent deformations of the wall, which can happen during natural disasters such as earthquakes. Failure doesn't mean that the structure completely collapses. It is also a sign of instability, which can increase the likelihood of it collapsing in the future. Below are some of the most common ways RSS walls fail, and they are sliding failure, bearing capacity failure, overturning failure, which is also known as limiting eccentricity, and improper drainage. And like the pictures on the right show examples of how RSS walls can fail, and it's the one with the bridges. And then on the far right, it shows you the limiting eccentricity, sliding, and bearing. Bill, next slide, please. So I'm gonna start off with sliding. The first mode of failure is sliding. Sliding is caused by the horizontal movement of the entire soil mass sliding onto the foundation zone. The most important consideration in proper design and installation of retaining walls is to recognize and counteract the tendency of the retained material to move downslope due to gravity. This creates lateral earth pressures behind the wall, which depend on the angle of internal friction and cohesive strength of the retained material, as well as the direction and magnitude of the movement the retaining structure undergoes. Lateral earth pressures are zero at the top of the wall and in homogeneous ground increase proportionally to a maximum value at the lowest depth. Earth pressures will push the wall forward or overturn, which is actually another mode of failure, if not properly addressed. Also, any groundwater behind the wall that is not dissipated by drainage system can cause a hydrostatic pressure on the wall. The total pressure or thrust may be assumed to act at 1/3 from the lowest depth. Sliding usually governs the design of the retaining walls most of the time, but overturning failure should also be considered. Um, it's very similar to sliding because it's caused as a result of excessive lateral earth pressure, and it causes the rotation of the wall about the toe. And this happens because of the exceeding moment um, of overturning moment compared to the overall sum of resisting moments. Next slide, please. Bearing capacity. The bearing capacity of the wall is influenced by many different factors such as soil strength, wall width and depth, soil weight, and surcharge and spacing. These facts are related to the loads exerted on the soil system. Some non-load related factors that need to be considered as well are things like earthquakes and any type of dynamic motion, frost action, subsurface voids, heave, soil erosion, and seepage. The bearing capacity is the ability of the soil to safely carry the pressure placed on top of the soil without undergoing a shear failure and large settlements. Next. Improper drainage. Some of the water that can build up without proper drainage would be inconsistent compaction of the fill soil, increased height of the wall, and use of clay backfill within the reinforced zone. When water accumulates behind a retaining wall, the lateral forces acting on the wall increase. The more water that has collected behind a retaining wall, the greater the hydrostatic pressure on the wall. The picture on the right shows a great visual depiction of improper drainage. You can see the rainwater during storms or runoff can percolate into the ground and eventually trickle down to the base. And the continuous buildup is what causes the hydrostatic pressure, which you can see the arrow pointing, which is acting on the retaining wall. Next slide, please. So loss of backfill sand can also cause failure of the RSS wall because when the sand is lost, it usually means that there's a significant amount of water that has entered the system. Water will enter through the top of the wall in like large quantities, and then it seeks a path through any breach in the filter fabric covering the wall panels. Piping usually occurs, and when this happens, it carries out sand backfill with the water. The loss of backfill is usually associated with very fine uniform sands. If the problem is allowed to continue, voids can form behind the wall face and sometimes cause precast panels to shift outward due to loss of anchorage. The joints of almost all of the MSE walls constructed in the early 1980s were required to be covered with filter fabric, and this allows water to pass while holding the backfill behind the wall panels. But if the filter fabric is compromised, either because of poor placement, deterioration, damage, then the backfill material may eventually find its way out from behind the wall. You can see the two pictures on the right. They show a really good example of backfill loss. And like near the base, there's a buildup of sand, which has escaped through the joints. Now I want to play a video of how water enters the wall. It's a company that creates jet filter systems to help mitigate erosion, but they made a really good video, so yeah, check it out. Um, okay. So next, I want to talk about how to improve drainage because it is one of the bigger issues. So gravel backfill for proper drainage, the first 12 inches of space behind a retaining wall should be filled with crushed stone or gravel. This like allows the water to get into the space to flow easier down the wall to the drains or the weeping walls. Soil compaction is also really important for creating strength, but it also makes the dirt less permeable, which reduces the ability of water to seep into the spaces behind the wall. Usually, for MSE wall systems design, they are assumed to contain free drainage, meaning that the water will be readily discharged through the soil mass and wall facing. But this can only happen if free draining soils and gravel are used in the reinforced soil zone. But if clays are used, which is not recommended, then they must be used in relation with proper drainage components. Pipe drains, which are also called toe drains, are perforated pipes that collect water along the length of the wall and drain it outside. Some of these are vented through the front of the wall as well, but others they run along the length of the wall and drain out at the sides. They're most commonly installed at the base of the wall, but in taller walls they might have multiple drains at like different heights. And the last one's weep holes. They're openings in the front of the wall that allow for moisture to escape. They may be positioned at the base of the wall for structures with minimal need for drainage or in like a grid-like pattern across the entire wall. The downside of this technique is that water flowing from the weep holes create unpleasant stains on the wall. So if the retaining wall isn't properly protected with like waterproofing overlays, varnishes, then that just leaves a stain. And yeah, I'm gonna pass the mic over to Shubham, and he's gonna talk about the advantages and disadvantages.
Thank you. Thank you. Welcome back to the presentation, guys. So here are the advantages of the RSS, the modern system of the retaining walls. So these are simple and rapid construction procedure, as we have already mentioned. So comparatively, the conventional reinforced concrete and gravity retaining walls, these are the pre-manufactured materials, rapid construction, and among different proprietarities, system has resulted in cost reduction relativity to traditional types of retaining walls. When there is a height of more than 10 feet or 3 meter, these RSS panels are more beneficial and more safer in terms of seismic resistance and loading. A study has been done on the observation on the base of the observations seismically active zones. These panels are more resistant to the seismic loading and result rigid concrete wall structures. Another advantage of the I, I'm sorry. So minimum traffic disruption during construction. In the previous session, I have already mentioned that we don't have to stop the traffic to repair the wall or to build the wall because we always have the precast panels ready to fabricate there. So we can store them on the side and the traffic can run. So no need of scaffolding. We don't need to build the scaffolding to support or to work to support the RCC constructions. So it's it's cost effective, and there are less deformation in this type of wall because this is not a single structure. These are many panels connected together. So if there is there is stress on particular panel or on particular point, that panel has to be replaced or that panel will show the mode of failure, not the whole wall. So I would ask the Bill to move to the next slide, please. Thank you so much. So the disadvantage, very less disadvantages comparatively. So it requires a large space behind the walls, not on the side, but behind the walls, because we have to give a face to install a requirement and reinforcement. And second, if there is a cut when we build our road or a bridge in the cut, then it has to have a larger space on the back to 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 fabricate these panels, and it requires a design responsibility between material suppliers and owners, of course, because these are precast members. So a design team has to talk to the owners or the suppliers very earlier in the earlier phase of the project. As we already have mentioned, the arc breezes that has a different shape. So we have to order them. We have to let them know what kind of shapes we need for the panels. And I think that's all for the disadvantages. Comparatively, advantages are more. This is more rapid, and especially one more thing: if there's a these panels needs a granular fill. That's a specific granular fill, standard granular fill. So if we don't have that available on the site in the local area, and we have to transport it from another place or a country or a city, that will take a lot of transportation cost. That can be costlier in that way. So if the material is available on the site or nearby in the local areas, so these projects can be very economical comparatively. uh, Thanks. I think that's all for the site. So there are the references. We have trick information. All credit goes to these websites and these links. Thank you for your time. If you have any questions, we are pleasure to answer your questions as much as we can do. Uh,
Thank
Hello.
you. Thank
You're
you,
welcome.
Shubham. Thank you, guys. Great presentation. I love the pictures on your presentation, and it was clear. So thank you very much. So let's get on to questions. So I just have a few. I have one question while we wait. Trong has one already, but with where you guys have all the pictures of the RSS walls, were those all from bridges, or most of them from bridges, other than the one that Shubham was speaking about, the one bridge? Are these all in Ontario, or Canada, or all over?
So yes, most of them. So breezes have a standard. Not even in Canada, but these pictures are from Canada,
Mm-hmm.
especially in Ontario. But all kind of breezes now. Uh, that's off topic, I think. But I'm from India, so
Yeah.
we have such type of panels in back home. I used to be
Oh,
like, yeah, I
that's
used
very
to be,
good
and
to know.
I was expecting like, what is this and how these are going to be stable. And thanks to you, ma'am, you gave us a chance to read on these subjects and to work on this type of panels and structures. I'm very thankful to you.
Oh, you're welcome. Okay, so let's get through some questions, and then I'll see if they get answered. My questions get answered. So Trong said, "Does water cause the material erosion inside the walls?"
Uh, yes, it does, because water has the ability to penetrate uh, in any material as long as it's not permeable. If there is a gap, even a hairline gap, or you can say 1 mm gap, so it goes through the material, and behind the wall there's all granular material, so water has a seepage. So as soon as it goes down, water has the ability to take the material out. Once it
Yeah.
get the space to come out, so it will take the material with this, and that would cause the reduce in the pressure, because the soil has gone out now. That was compacted to the maximum density. That's the MDD, maximum dry density. That's going to reduce now, and that will cause the failure of the structure.
So will the whole structure be failed, or what part of it? Because remember when you
So
said earlier,
this
just
is
a
the
part of
advantage.
it would.
This is the advantage of this type of RSS walls, as
Yeah.
these are the panels. So where we see the seepage, the nearby one or two adjacent panels would be affected, not the whole structures. As Bill already mentioned, it's no failing the structure doesn't mean it has to collapse.
Yes.
Even if we see one or two panel is collapsed, that's more concernable.
So when you were doing a review, did any of you, not just Shabam, anybody in the group, come across anything when they actually replaced the panels when they failed, when there was failure? I think who was speaking about the failure? Was it Bill?
Is Bill there?
No, that was me. Prem.
Oh, Prem. Sorry, Prem.
No worries. Yeah, like I came across where they usually like fill the voids and they seal
Yeah.
like the surface joints. It kind of stops the like the backfill loss, but it like if it happens in one place, it usually continues on like at other joints and stuff too regularly. So it has
Yes,
to
of
be
course, of course.
maintained really well. It I think it mainly happens when the filter fabric isn't applied properly.
No, no,
Uh,
no. But what I'm saying is that can it be replaced? Like,
Yes.
did you come across actual replacement of a panel?
no.
No, you didn't come across. Okay, that's fine. That's fine. Okay, so let's go to the next question. Thank you, Prem. Thank you, Shabam.
Yeah.
Next question, Valeria. She's asking, is it possible for any grade of backfill to be used during the construction of RSS walls? So,
That's a clearly no, I think.
So no,
yeah,
sure, can I take
Okay.
this? Thank you.
Keeper,
All
Yeah.
right.
go ahead.
So no, any grade cannot be used because it has to pass a sieve test. It has to have 8% passing in the 0.0075 millimeter sieve size, and it also has to be well graded because it has to have free draining so that the erosion can sorry the water can erode freely through the grains without causing failure. So it has to meet the requirements.
Yes, the more fine the material, there are more chances of the failure, because the finer the material, that's lightweight, and that will move with the water. So
Great. Thank you, guys. Thank you very much. That's true. I agree with both of them. Okay, Daewoo, soil compaction is required to backfill retaining walls. Is geotextile, yeah, sorry, if geotextile is applied, does it place to every compaction layer? So do you place geotextile? Sorry, I'm
Yeah,
confused about
yeah.
the question.
I,
Bill, you
I,
know,
yeah, I can answer that question.
okay, go
So
ahead.
so when I was talking the layer by layer section, so when
Yeah,
each row of panels are installed, let's say for example the first layer of panels are installed, they're both directed on two sides, and then you put your uh, fill, which is going to be reinforced by the geotextiles, and then compacted, and then after that you install the second layer, and then it's also proceeded. The same structure keeps going on again until you reach your desired height of panels, and then you cap it off, and then you continue on whatever road is connecting to it. So yes, uh, it does apply to every compaction layer.
Thank you, Bill.
Yeah.
Okay, so how do you prevent the backfill from leaking out? Yes, that was a good question. That was actually one of my questions.
Yeah. So you go ahead, Keith.
Yeah. All right. All right. I just like to add what mentioned earlier. The backfill once the right grade backfill is used and it's compacted, worrying about it leaking out by, let's say, road runoff and water through the drainage pipes, worrying about it leaking out is highly unlikely. It usually leaks out when it is well dense. That's after failure within the soil compaction, which is highly unlikely. But Bill, you can add to that if you want.
Yeah, that was what I was mentioning earlier actually about like the backfill. So I mean it's definitely likely if it's not built properly, but filling the voids and sealing the surface joints is usually what halts like the backfill loss. But again, it is temporary, right? So it has to be maintained regularly.
Okay,
And also to
perfect.
add, during the construction phase, to prevent backfill from leaking out to your vertical or horizontal joints, uh, you apply what's that called? Like a spray, a glue spray, and then you put on a geotextile joint material, like geotextile fabric, over those joints, so it prevents uh, the materials to leaking out. Yeah.
Great, thank you. And last question, and then we'll take a break. So similar to shoring to prevent collapse of the panels from sliding, do they use tiebacks to prevent these panels from failing? Do they use tiebacks on top of similar to shoring to prevent collapse of the panels? Yeah. So do you guys or is tiebacks used to prevent these panels from failing?
Uh, I'm sorry. What the question is, ma'am?
Are tiebacks used to prevent panels from failing?
Yes, tiebacks are
They are
used.
used.
Yeah, and
Okay.
these all panels are interconnected inside
Okay. Great.
on the filling side. These all are interconnected. There are ribs and there are hooks to connect them.
So what if let's say there's a failure, well, if there's the water leakage, there's poor water, um, what was the question? I had something down. For any improper drainage, can it be fixed after the wall has been complete? So if we find that we have improper drainage and it might actually cause failure, is there any way to correct that?
Yeah.
Uh,
Um.
yeah, Bill, go
Um.
ahead.
Yeah. Sorry. In the last video shown by, I think that was during Prem's presentation.
Yeah.
There was an engineering solution that was shown, where they used this type of syringe, what's it called? It's a
Like a
jet
mesh
filler.
thing?
Yeah, yeah, used to basically plug into the hose and take out all the moisture inside of it.
Ah,
Um,
yeah, I saw it, but it kind of stopped, so I wasn't sure. Yeah.
oh, yeah. It has to be tackled early though, before the
Okay.
failure.
Before
So,
it goes into failure,
so
of course. Yeah.
once it's constructed, you know, it will take a while before it buckles and fails. You
Yeah.
can see it before it happens, really.
Yes. There would be a sign that there would
Yeah.
be the water and the fill would come out, and there would be more pressure on the outside, the front face, and you can see the joint is going to open. Slowly. If the joint is going to open, that means there's a water inside, and that's trying to push the fill out.
I see. Well, good. Thank you very much. It was a very informative presentation. So thank you again. So why don't we go ahead and take a 10-minute break? We'll come back for 4:30. Okay, guys?
Okay, okay.
At that point, we're going to just kind of do exercises for 3D. But again, thank you guys very much. Okay, and I already saw that you submitted it, so great. Okay,
Okay,
let's take our break. Okay, thank
okay.
you.
Take care.
Hi, everybody. Okay, so did any of you use or utilize time on Tuesday to look at the 3D components now? Excellent. I think it's a little bit longer for the 3D, longer than the 2D, if I remember correctly. But let me just share my screen. We'll get started on how to open up 2D at the 3D, and then why would I do that? Sorry. So Arifin and everybody, you guys need to join through the school. So you need to when you join, hold on, I'm gonna get you should not be doing it as a free trial. You should actually be logging in with your student information, and it should allow you to automatically access it. So let me see if I can get it here. I'm going to open it up on my end. Okay. Okay, so do you guys, let me just go home here. I'm not sure if this, can you let me know if this works for anyone? Guys, I just put a link in. Can you let me know if it's working? I can't do a Dropbox for it, Trung, because this is part of LinkedIn Learning. I can't download the video and place it on my own thing. So, hello, guys. Can anybody let me know if this link works? Okay, so when it works, does it open it under your name? Does it open it under your name? When you see me, you see at the top there, it opens it under your name. Okay, so if I was to give you this link now, would this link work? Does this link work straight to the 3D training with Dr. David Martin? Excellent. Okay, good. And it's under your name. It says me, and then if you click down on me, you should be able to see your own name, correct? Okay, so that's how you're going to get your training. Save that site, and I'm going to upload this link instead of the one that's online right now. I'm going to update it right now so I don't forget, because my brain has, a million things in it, and I don't want to forget what I need to do for you guys. So remember, this is also 3D. Sorry, this is also worth 5%. So I just updated it, everybody. Okay, for the 3D online. So if you don't get it here, it's online as well. So you're going to have some time to do that. So we'll just go through how the difference in no, you need to submit it online. Just Oh, a Dropbox on Blackboard. I was thinking, yes, I can. Of course I can. So just you're welcome. Let me do that today. You guys, some of you are finished. I know I gave you time, so I'll do that for you guys today for sure. Okay. What else do we need to do? There's so many things. Okay, so for 3D, we're going to go through how to open the seed file for it, and basic drawing for it, and then you guys can try and create do it yourselves. And we're just going to go through some things, and then of course after that you can have the rest of the time to continue with the course, since you guys, some of you couldn't get access to it. You can do that. For others, you can continue working on the exercises, trying different exercises with extrusions, and that will kind of be it for today's class. Okay, we only have about a half an hour, so we don't have much time anyways that's left. Any questions? Okay, so I noticed while we were in the middle of presentations, a lot of people came in. They didn't tell me. I know only 2 people kind of said we're here. So I know you said, oh, sorry. So the final will be in 3D. So the final project is going to take that 2D project that I still have to mark, okay? And then it's going to change it. You're going to take it and, make an extrusion out of it. You're going to make it into 3D. Okay, so that's how it's going to work for project, for your final project. Okay, and then that's it. So you're going to work on your final project from next week all the way until hold on. So you can submit it on the week before your proficiency test. So and then you'll have your proficiency test on the final week, and then that's it. So those are the final 2 things that we have. Okay. Any questions? Any other questions? Okay, anybody who came in during the presentation that want to let me know so I can mark them here. Thank you, Zara. Okay. Okay. All right. So, start off. You're here? Thank you, Ryan. That was very delayed. No. Green. Okay, so I also noticed that I've been saying names wrong, like Bilgan. Have I been saying your name wrong? Renique, I've been saying your name wrong. Even Shubham, I've been saying your name wrong. So I apologize. Please let me know when I'm saying your name wrong. Help me fix it so that I don't. I apologize ahead of time. So just correct me. Correct me. Okay? Please and thank you. I'd appreciate, if someone asked me how to say my name correctly, because yeah, I can understand. It can get a little frustrating after a while. So I apologize if I do say your name incorrectly. Please all just let me know and I will try my best to do it. Okay. Okay. So let's go share my screen. That's what I've been trying to do for a while now. Okay. So when we are going to access our new seed, okay, because we're going to be looking at 3D instead of 2D, we need to open up a new, file. So for us to do that, you're going to go and create a new file here. And this will open up new. It will ask you what your new file is. and we're going to need to change the seed to 3D. Okay, so you're going to click on Browse, and you're going to need to change it from seed 2D to seed 3D. Okay, once you've done that, you click Open, and then you give it a name. So you could say exercise, is 1 and 3D. Okay, whatever you want to name it, and then you can click on Save. Is everybody okay with this? You guys need me to repeat it? Okay. So I'm going to close this down. I'm going to open up MicroStation. When I get here, when you open up MicroStation, it's going to ask you for your file because that's the way MicroStation works. You're going to click on New File. Then you're going to go to Browse for your seed. So you're going to click on Browse, find seed 3D, click on it, select it, press Open, then give your file a name. So exercise 3D, and then just press Save. Once you press Save, you're going to go here now, and then you can select the exercise 3D, and you're going to click on Open. I don't know why I'm getting this. I hope I'm having issues, so I'm going to have to deal with this, but hopefully you guys are not having this issue, and then it will open it up this way. You'll have a tiles for your views. Instead of just the one big one, you're going to have tiles for 4 different views. Did everybody get here? I'll give you guys a minute to get here. Okay. This is your top view. So when you're looking at plan view, for example, okay, this would be it. I'm going to turn off these ACSs here. Okay. Here is your isometric or your 3D, okay, view. And here is your front view. And then the right view as well. Okay. So you have all 4 views. That's all you really need to be able to see whatever you want to work with. You have the same kind of tools, okay, for drawing, your same drawing tools. You have other things for modeling, but we're going to go into the feature modeling. And we're really going to be using here where we're going to do the extrusion of the features and a few more things as we go along. Okay, so you'll use these as you do your project, but let's go ahead and just kind of get started. We'll draw out one of these exercises. Remember the exercises we were doing at the beginning? Some of them were 3D, some of them were 2D. Well, we're going to take, a 3D one, we'll do that one, and then you can do some of the 2Ds that you had. You can work on those and make them 3D. So we're going to look at this one, and we'll draw this out, and then we'll see how to extrude it, and then you guys will have the practice time after, okay? So first thing you're going to do is draw. You can draw in 2 places. Depends on how you're going to extrude it. We're going to extrude it from the top. So what we're going to do is create the front view, okay? And then we'll do the extrusion after through the top view, okay? So I'll be working in the front view, and you'll see how it will look, okay? I don't like these very much. Okay, so I'm gonna go into and also when you want to do anything with 3D, you want to make sure that it's a joined line. Okay, you can create them in a regular, single lines, but at the end you're gonna have to create a complex shape, or you can, go on for placing a smart line. Either one will work as long as at the end the shape is one line. Okay, a joined line, so a complex shape. Okay, is that clear, everybody? So for your project, you know, all your lines are eventually going to have to be joined so that you can create your 3D model. Okay? Sound good? Okay. So let's go ahead. So I'm going to get started. I'm not going to, doesn't really matter about the units right now. And you can see here, when I click on the front, you can see it in all the views. Can you guys see that? You can see it on the side here, on the right-hand side, the top view, the isometric view. And as I keep drawing, you're going to continue seeing these lines. So my first line. Okay. Now there are people who can automatically, draw it automatically in the 3D here. Sometimes it's easier, sometimes it's hard, sometimes it's easy after you have something, and then you can correct it and do all these things in the 3D. But let's just get into the basics. Okay, and as I'm drawing, can you guys see here what's happening? Okay, so if I select my fifth view, so it automatically just shows me one line from the top, which makes sense. And while you guys are in fifth view, you can just click inside each of these views and it will kind of bring them closer. You guys see that? So while you're here, you can see that my, front view is kind of isometric a little here. And then here again, just one line, because we haven't really done any extrusions. We haven't created that 3D model. Okay. So for us to create it, we're going to go into feature. We're going to click on extrude feature. And here you have the option of extrude it by, a distance or a thickness or a certain angle or anything like that. We're just going to do it by distance. And the distance is 1.5. Okay. And that's this distance right here. Okay, guys? All right. So once I have that, I can just click anywhere. And it will automatically extrude it. Do you see that? And I want to just get rid of this here so that you see I can do it on this side, I can do it on this side. It doesn't really matter. Okay. Once I've clicked on the side I want it, it becomes a 3D object. Okay. Everybody see that? Now, you can make it look differently by having your display style changed. And usually smooth is the best one, with showing visible lines and hidden lines so that you can actually see that. And then you can change, of course, the color of your line depending on what it will be. Okay. And you can click on the one that you want it to be. So here. And it will automatically change it. So once I select the view that I want to have it changed and I double click on it, it will automatically change it. So now you can see that it has my hidden lines. Depends on which view I look at it, it shows me different hidden lines. Okay? So that's it for that. And you can see that while I'm working in my isometric view, there is also, before we had X, Y, now we have X, Y, and Z, and that's for this. So when I want to actually make some changes, I could work in here to make, more changes if I need to, or to, if I want to make it a little bit thinner or a little bit higher or whatever, like I can select this and do it. I can widen it up, things like that. If I find that maybe the size wasn't correct, I can always do it through 3D. But until you're comfortable with 3D, you can still work in your other views. So whatever you work in here, you'll see through here, or you'll be able to see in also your right view. Any questions? Okay, we only have about 10 minutes, so you guys can go try it out. Okay, if you do have a question, let me know. You have until next week to kind of play around with all your exercises, get comfortable with it, and also listen to the 3D video, or watch the 3D video, and then you can get started on your project next week, and then we'll do the same kind of thing as we've done before. We'll have our team sessions and our class. So that's it for that. Okay. If there are no questions, you guys can continue, practicing. And if not, and you're going to leave, have a great evening. And I'll see you all on Tuesday. Thank you. And thank you for the presentation again today. It was really good. Thank you, guys. Have a great evening, everybody. So the one on the top left, top right. So this one, this is the isometric view. This one that's highlighted right now, Hassan. You're welcome, everybody. Have a good evening. This is the one. Okay, Hassan? This one is just the top view. This is your front view, and then this is your right view. Don't be sorry. It's new. Any other questions?